Okay, so let's go ahead and get started. I'm delighted to introduce a very good friend of mine, Chris Gorgolewski, and Kat. Chris is really one of the pioneers, maybe the principal force behind BIDS. If you haven't heard about BIDS, we will have a talk later in the week talking all about it. It's the brain imaging data structure, and really has made major contributions to the neuroimaging informatics community in all kinds of ways. And he's been a contributor to Neurohackademy for the last few years, I think every year actually. And I won't embarrass him by going into any more detail. Let's just go ahead and get started. He'll talk about Docker for scientists today. So take it away, Chris.
Hey, thank you. So warm welcome to everyone who's here. We have a Q&A thing here in this very lovely Zoom. So I will monitor the Q&A, and because it's such a weird times, and I'm also just woken up and barely functioning. I would love you to please wake me up with all sorts of questions. And we're gonna get started. I see there are 58 people here. I will obviously try to learn all of your names. Warm welcome to Gabriel, Julia, Kale, Mathuri, Markiewicz. Yeah, that one's a tough one. Yeah, okay. So enough of this rambling, and let me start with the presentation. Okay, so we're going to talk about Docker and other software containers for scientists. Before we begin, I would like you to navigate to this website, and I'm going to go ahead and post this link to this Slack as well, so you would be able to see it. Sorry, this is those are the basic steps and that we're going to be following later on, because this class is supposed to be very practical, and this will allow you to basically stay on track. Okay. Here it is, and yes, the Adam Ritchie Halford asks whether all scientific talks should have cat gifs. Oh, actually stated that all scientific talks should have cat gifs, and that is obviously true. It's a new mandate. We all adhere to it. Okay, cool. So we're going to be following this later, but before we go to the practical part, let's talk a little bit about theory. So the purpose of software containers is to contain things, the same way as this cat is containing itself in this container. Let you take it in, the cuteness and craziness of this image. So a brief history of trying to contain and trying to encapsulate things in computer science starts with virtual machines. Virtual machines are a fairly simple concept that involves simulating a computer with all of its hardware interfaces and hardware components inside another computer. So for those interested in cognition, it's a little bit like theory of mind when a brain is simulating another brain. But in practice, it is basically what I just said, where you have these virtual, as in simulated in software, hardware interfaces like network cards and CPU interrupts and stuff like that. and you expose them to another operating system. So this allows you to run one operating system inside another one fully. They don't share anything. The operating system that is being simulated knows nothing about the operating system that is simulating. And this is quite useful for debugging things. Let's say, imagine that you are responsible for testing whether a certain application works on all different flavors of Mac OS X. And instead of having, 16 different computers, physical computers with different versions of Mac OS X, you run these virtual machines, 16 virtual machines, one after another, and each of them has a different version of Mac OS X, and you test your whatever application inside of them. It's also useful for demonstrations. We actually use this technology for teaching once at a course in Beijing when we had a virtual machine image that we gave to all participants with all of the different types of software that is necessary to do neuroimaging. And this way we're able to run a hands-on workshop using hardware provided by students, their own laptops basically, without spending too much time installing all the individual pieces of software. And that theme of being able to encapsulate your environment or all of the different applications and all of the different pieces of software that you need for your work is the main advantage of software containers that we're gonna try to learn today. So as I said, it's a whole computer simulatedness in software. That's what the virtual machine is. And it's fairly slow, but improving because you have to simulate a lot of stuff. The images are fairly big because there's no software being shared across the different images and between the simulated and simulating machine. It is fully encapsulated. In other words, that because everything is simulated, there isn't anything that you cannot do inside the virtual machine that you can do on bare metal OS installation, which is very useful for being able to test all sorts of different low-level pieces of software. It's also a little bit slow in terms of booting it up, suspending, resuming, because it has to go through this whole boot up process when you start it. And that makes it a little bit less convenient for quickly iterating. So those are virtual machines. If you have any questions about virtual machines, there is a Q&A where I will be happy to answer any of those questions. So don't hesitate to use it. Okay. And wait, sorry. But to understand the current landscape of software containers, it's good to understand the different needs of different stakeholders. So basically, at some point in the near past or recent past, to be more grammatically correct, renting virtual servers in the cloud became easier and cheaper. And that also meant that setting up servers, spinning up those virtual servers in the cloud was much more common, and people started playing with more sophisticated infrastructures. And it turns out that managing the configuration and setup of all of these different services, such as HTTP, SQL, DNS, spread across multiple hosts, or even shared on a single host, was non-trivial, and each time you have to set it up on a new cloud provider or a new virtual server, you have to make sure that it's all configured the way that it should be configured. And that was a bit of a problem. So if you find it hard to relate and a little bit confused with all of these like virtual servers, cloud, DNS, and all of that, imagine the following situation. You probably have certain set of applications installed on your laptop. And you are used to things being set up a certain way. Maybe you have a background with a cute cat, and maybe you have a special app for taking screenshots that you really like. And it's fairly similar when it comes to running web servers, such as like Neurovault, OpenNeuro, or some other web servers, or things way more complicated like Facebook. They also need to have all sorts of different pieces of software installed and configured in a specific way, and they depend on that configuration. So being able to automate the setup allows engineers to basically avoid making mistakes, because you don't have to set all of these things up quickly. We have the first question for the audience that makes me very happy. Nicole asks, what are the main differences between Singularity and Docker? Would you recommend one over the other? It's a great question, and we're gonna go over it. We're gonna try Docker, we're gonna try Singularity, and it's gonna be glorious. And at the end, we'll be able to talk in depth when is it good to use one and when is it good to use the other. Great question. Thank you, Nicole, for breaking the ice. All right, but a little bit more theory before we get there. All right, so we talked a little bit about virtual machines. Let me just quickly make sure that I am on the right slide. We talked a little bit about virtual machines, but the response of the industry to their needs to help set up these services or even microservice services was to come up with something called containers. So containers are trying to solve a similar problem to virtual machines, but they are a form of what is called a kernel-level virtualization. So instead of simulating the whole machine with all of its hardware, they share the kernel with the host machine. So kernel is this low-level piece of software that understands and talks to the hardware and exposes some very low-level functions, such as open file, read bits, open network socket and read bits, and stuff like that. This kernel is, as you can imagine, very important, but it also is a form of, it's basically an interface that allows you to abstract away hardware. And it's very crucial for operating system being able to work on different pieces of hardware. So the kernel allows you to go and buy a different notebook that is made by a different manufacturer, that has different network card, maybe has different graphics card inside it, and the operating system still works on it. You don't have to install a different operating system because the kernel is virtualizing this, or in other words, kernel is translating between the idiosyncrasies of different hardware. So containers take advantage of this. And because they are virtualized on the level of the kernel, they are faster than virtual machines. The images are more or less the same size, virtual machines, but there are some very nifty tricks where images can share some of its content. So containers can be built in layers, and can be composed one on top of another, and those layers can be cached and shared, which saves some space. And space in software containers can be a big thing, because as you can imagine, storing all of this software can take a lot of space. All right, so a little bit of a graphic here on how this is different. So on the left, we have a virtual machine. And what we are seeing here, that guest OS, the purple thing, that's basically all of the kernel stuff. And with the virtual machine, you have this purple stuff, the kernel, twice, because the server, the host, has its own set of kernel software, and then it simulates a whole hardware machine, and then each of the virtual machines have their own set of kernels that talk to this virtualized hardware. So when you do something in a virtual machine, you go from you talk to the virtual machine kernel, which talks to the simulated hardware, which talks to the host machine kernel. So that's why it's a little bit less straightforward. And the container, this is simplified because each of these apps, each of these containers are talking to the host kernel directly, because as we mentioned, the kernel is shared between containers and the host system. We have another question. Nick is asking, can you define what is meant by an image? I have not been able to figure out what this means within the context of containers. Yes, so this is a little bit confusing. And I can relate to this confusion, and I'll try to make it a bit more clear, and with the magical power of coffee, I hopefully will be more consistent with the nomenclature as well. So you probably heard two terms, containers and images. And they're relatively sort of related to each other. An image is a snapshot of all of the different libraries and all of the different pieces of software that is being used in your environment. This is the snapshot of your environment, and it's reusable. So you can, and I'll show you how to do it. You can browse a library of different images, and can take that image and run it. And when you run the image, that's technically called a container, because then that image becomes live. It goes from a static picture to something that you can interact with. And that's the sort of main main difference between an image and a container. I don't know what's a very good analogy for this. Maybe I'll come up with something. It should be a little bit easier to understand when you start actually playing with these images and containers. But for now, an image is a collection of software and libraries that encapsulate software environment. And a container is an instance of that image where you actually start running it and you start playing in it. So you can have one image and run multiple containers using that image, that one image. And it goes more complicated because then you can take an image, run a container, and change something inside it and take a snapshot of that, creating another image. So, but we'll get there. And there's a follow-up. Virgil suggests the analogy could be classes and instances. Yes, this is a good analogy, going from object-oriented programming. And an image is a class, and an instance of that class would be a container. Thank you, Virgil. For those familiar with object-oriented programming, that could be a good analogy. Okay, and Gergen also asked, am I right that when I use container, I can run it only with the same OS as host OS? Also, what is hypervision? Thanks. All right. So, okay, I can do thumbs up. Yes, like thumbs up, virtual comment. Okay, cool. Yes and no. In general, yes, and there are some ways to work around this. When we talk about software containers, it's because we're sharing a kernel. This kernel needs to be compatible between operating systems. Without any special hacks that recently have been made and are very straightforward to use right now, it was not possible to run software containers that are predominantly a Linux technology on non-Linux operating systems, because non-Linux operating systems had a different kernel than Linux containers, and these two things just didn't work. So that's basically is the answer to the question. So they have to be compatible. Although right now we have very good, very efficient workarounds to this problem. Both implemented in Windows and implemented in Mac OS X that allow you to run Linux containers on those operating systems in a fairly straightforward fashion. If we're gonna have enough time, I can walk you through how they made it happen and how it's actually working underneath. But I don't wanna provide too many details that can confuse a little bit. The bottom line is that in principle, because we're sharing a kernel, container operating system and the host operating systems have to match. But right now we have very convenient workarounds built into Mac OS X and Windows that allow us to run Linux containers on those operating systems without much of a hassle. And hopefully this answers your question. As a follow-up. Well, I only gonna also answer the question about the hypervision. The hypervision here is basically simulating the hardware, and let's stick with that for now. And there's a follow-up from Virgil. Could you produce an image in Mac OS X and deploy as container in a Linux server? Yes, you can. Because of these workarounds, you can create a software container image that is a Linux type image on Mac OS X and deploy it on a Linux server. You can also deploy it on a Windows machine. And that's the beauty of it. We can use these containers across different operating systems. And I'm going to show you how to do it. This is one of the workflows I'm trying to encourage you to do because it's very convenient when you, for example, build an image, create an image with your environment locally on your laptop when you're developing or when you're prototyping something, and then you want to run at scale, either in the cloud or on a high performance computer. And you just want to make sure that all of the dependencies, all of the different pieces of software that you used are there. So you can create it on your Windows or Mac machine and then use it in your high performance computer. So yes, okay, thank you so much for all the questions. This makes me feel that I'm less like shouting into the void, which is great. Nicole asks, what are the main differences between Singularity? Well, sorry, that was already there. Just things got reordered. Okay. I think we've answered everything. All right, cool. And yes, so I'm gonna answer live. Okay, I'm gonna move on. Okay, so So next step would be explaining finally what is Docker. So Docker is the most popular software container implementation. So I'm trying to be a little bit agnostic because Docker is not the only one, the only implementation of this idea of sharing a kernel across instances. But it's the most popular, the most convenient, and this is something that is worth investing your time into, and it also has a lot of work done for it that that allows us to be more efficient. Basically, they've put a lot of effort into making it work on Windows and Mac OS X, so that is convenient for us. So the two sort of main broad stroke components of Docker are the Docker engine, and this is the bit that downloads images and runs containers. And Docker Hub, which is a centralized web service or repository for storing and sharing container images. And the fact that Docker provides these two things and they're very well integrated is super convenient. And I'm going to show you later how and why. Excuse me. Yeah, because having this repository of images allows you to share your images with others, to share it with yourself as well, to basically have this external storage of images. As you will notice while using this system, they can get very big. So it's quite convenient to be able to just remove things that you don't use right now and be able to come back to them later. And Docker Hub as this repository, which is completely free, is super convenient for doing this. Okay, so, and now the big question here is like, yeah, Chris, all this mambo jumbo CS, boring, right? Big question is like, why should scientists really care about this? Like, what is this useful? Like, how this helps me with my next Nature paper, right? And the real answer is it really doesn't, right? But because that's not the point of Nature papers. But what it can help you is being more efficient and more diligent and less error prone as a scientist. So basically, containers are very useful for capturing and sharing complicated set of binary dependencies. So if you are venturing into using, like maximizing the flexibility of different types of analysis simulations or whatever you're doing, and you are depending on software that comes from different sources and different environments, you're like mixing Python and R and maybe using a bit of FSL and maybe some type of SPM in it as well, you will end up with a hairball of different dependencies. And that might be hard to manage because you're going to write a certain set of scripts that depends on certain versions and depend that, like, sort of make sure that all of these different things are installed. So software containers can help you manage that because they capture this whole environment. They basically encapsulate all of the different things that are installed, of the libraries that are installed. So you can take this environment, create an image based on it, and use that image for your research and make your research basically more reproducible. So one, for people who are familiar with Python, this is sort of a similar idea. It's like a virtual environment or virtual env, but on steroids because it works across all the different languages because it's not just Python, it works for R and works for basically anything that is a library. And we have a new question, which are actually two questions. Almost like two questions in a comment, right? You know, it's like go to a conference, someone has two questions in the comments and turns into a half-an-hour discussion. All right, let's see. Two questions. Are there licensing issues with creating and running images? Say you would like to create an image with commercial software and run it in another machine. Well, yes. So it's not a magical sort of like, oh, the law doesn't apply inside containers. No, it's like if you have a piece of software that says you can only run it on one machine at a time, it doesn't matter whether you run in a container or not. It's it's one machine. It's one machine. So it's not. Yeah. So laws still adhere. You have to adhere to laws and license agreements when you use containers. So this is mostly, practically speaking, you're gonna run into this with MATLAB, right? So you can put MATLAB inside a container and you can run containers with MATLAB, but you still have to deal with licenses, right? This is not a way of making MATLAB free. And you can deal with this. You can still have containers that talk to a license server or gather the license from some external source. So this could be worked out. And the second question is, if you create an image on a Windows OS laptop, then run it on a Linux-based high-performance computing node, can I access more memory, CPUs, and GPUs on the larger compute node than were on the laptop? Yes. Yeah, a big yes. This is the big advantage of it, and I'm so glad you've asked. Yes, you can. That's basically the workflow. You prototype your workflow. You prototype your script, your analysis on your laptop, and you capture this whole environment, all of the dependencies of the libraries, and maybe you prototype it on a small chunk of data, and then you create an image. You take that image into an environment that has more RAM, more CPU, more resources, and you just run the same script in the same environment. You don't have to install everything and make sure that talk to admins and whatnot, and it just runs with more resources because there are more resources. So there are ways to control, like limit how much resources are available to an instance of an image or to a container. But by default, all of them will be available. I hope, Alberto, this answers your question. And there's a follow-up. Do the license keys files get incorporated into image automatically? No. I don't think there's any automation for that. There are some ways to bake in license keys into images. And that is possible to do. It's not very hard. Tinashe, I apologize if I bastardize your names. You can complain about me on Slack later. Tinashe asks or states, actually, it's possible to add arguments to the command that spins up your container. You could imagine creating an image with MATLAB and no license configuration, and then when the container is used, it will automatically license itself using a file argument. Yes, so that's one way. You can make, basically we're going to go through that in practical, how containers can access files from the host operating system. All right, cool. Hope this answers your question. And I'm gonna mark it somehow. Yes. Oh, Dorothea asks, could you give an example of binary dependency and what's different from normal dependency? Okay, good. That's a great question. Yes, I throw around this this term. So when I say binary dependency, I sort of meant something that is already compiled, like for example FSL. That is compiled, as in you get a binary blob. It's not a text file. It's not a script that you can open in a text editor. It's a binary that is distributed from Oxford. So that's what I mean. So FSL is an example of such dependency, and the core registration software is another example of such dependency. And of course, Docker is not limited to only such dependencies. It encapsulates anything. It encapsulates also data dependencies. If you have, for example, you want to put in your favorite atlas or favorite parcellation inside there, you can do it as well. So that's not a limitation. That's sort of where it excels. Like if you, So I was trying to point here a difference between capturing dependencies that are, for example, pure Python. They're all just basically scripts, basically text scripts.py files, and things that are not pure Python, such as FSL and things like that. Hopefully this answers your question. If not, please let me know. Okay, now, okay. So with Docker, does bin dependencies need to be wow, this is moving and with Docker, does binary dependencies need to be compiled when running the image, or can they be compiled beforehand? They can be compiled beforehand, basically. So you can just put in blobs of binary stuff in it. So think, yes. And I'm gonna mark some of these down because I'm getting lost in them. Okay, Steph is asking, does it make a difference on the reproducibility of result whether you run Docker image on a Mac or Linux machine? I have this paper in my Grosenschild et al. 2012 that showed that FreeSurfer is all different on Mac and Linux, even when using the same FreeSurfer version. So I was wondering whether this issue also applies to Docker images. So yes, yes and no. So there are slight differences in terms of underlying kernels that are being used when you run the same container on Mac versus Linux, but those differences are much less than the differences between the host operating systems. And the main, if I remember this paper correctly, the main difference was between like Little Endian or Big Endian between these systems. I'm not completely sure, but I would expect the differences if you use Docker for it, the differences would be way, way smaller. And also, please remember that many of these algorithms, including FreeSurfer, are stochastic by nature. So if you run it twice, you're not going to get exactly the same results, even if the environment is exactly the same and the input data is exactly the same. So there's also some level of sort of background noise, so to speak. So to sum up, the differences will be much smaller, but there's still some small potential differences in terms of what kernels will be used. But yes, if you care about this reproducibility, using containers will mitigate the problem to a great extent. Thank you for the question, Steph. And okay. And yes, I'm going to mark it. Yes, if I didn't answer a question and accidentally marked it as done, please ask it again. I'm sorry. The coffee is still not working. All right, let's move on. So someone asked an example of a binary dependency. So this was taken from the Connectum pipeline or HCP HCP pipelines, and they had these very specific, at least at some point in the past, I don't know, it's right now, a very specific instruction of installing stuff. They basically said, you need to have FSL, but version 5.0.6, not versions 5.0.7 because we're not compatible with that version. And then you have FreeSurfer, but not the normal FreeSurfer, but the HCP versions of a FreeSurfer, and not the 6.0 version, the 5.3 version. And you can see where it's going. It's basically, they've got this great pipeline, it works very well, but it requires these very specific versions of software. So this is a perfect use case for a software container image where you could just package all of this into a single entity, into a single image. And when someone runs this pipeline, HTTP pipelines, it basically has everything it needs with all the versions it expects. So that's basically a good example of where this is useful. Okay, let me just, yes, there's one more use case that is interesting that I want to mention very briefly. Often we do analysis over many months, and it's useful to be able to have project-specific software environments. So let's say you have a certain project and you have a pipeline for it, and you analyze the data, and maybe it's a longitudinal study, maybe participants still come in. Maybe you just submitted the paper, run the analysis, submit the paper, but you know that reviewers will come back, and reviewers being reviewers, they're going to be like, oh, have you tried modeling motion in 27 different ways? And then you have to reanalyze some stuff. So it'd be good to be able to jump back into that environment and quickly make the changes and run everything. So containers allow you to do this because you can capture those environments and you can switch between them. So you can have an image for every project you have and not be limited by, you're not like constrained in a way that you're not allowed to upgrade any software until this project finishes, until these papers get accepted, because you have an image for each project. So you can have a different version of software in each of these images, and you can quickly switch between them. And you can also have these images shared across your lab members. You can give it to people and make it easier for others to sort of ramp up and start. Okay, hopefully this motivation is useful. Okay, so now we're gonna go to the practical part of this exercise. Tal, are you still there?
Yep.
Is there like a way of to do like a vote?
I think there is. 1 second. Oh, unfortunately, I think it might require either one of us to log in, but let's see. Oh, no, okay. I think. Take me a little while to figure out, unfortunately. But I can work on that if you keep going. Also, you might want to take a 10-minute break at some point. Actually, maybe if this is a good time to take a break, maybe we could do that and then.
Yeah, let's do that. Let's take a break, and of course, if you have questions, please shoot, and then we will we'll come back and try to figure out any potential installation issues and go into the practical part of the exercise.
Right, so let's say 9:55 if folks want to be back then.
Okay.
And I'll figure out how to run the poll.
Okay.
Do you want to, I think I have to do it. Do you want to tell me what the poll should read?
Yeah, so it's a quick question. Does Docker work on your machine? Yes, no, I don't care. Or maybe yes, no, I'm not planning to follow. Thanks.
Okay, I should show up now. If you go to polls. Oh, sorry, there now it's launched. And that's anonymous, so don't worry about anyone finding out that you like squirrels more than Docker.
Hey.
Chris is partial to squirrels, hence the.
Yes, I am.
It looks like most people have, well, most people have responded at least, are able to get Docker working.
Hosts and panelists cannot vote. But how do you see the...
Do you feel the need to vote?
No, but how can I see the answers?
Oh, you could, maybe only I can. Well, I'll tell you. I might lie, but I'll tell you.
Okay.
We'll just give it until the end of the week.
Brian says maybe yes, no, working on it. Well, but squirrels, right?
Only one response from squirrel. Very sad.
Only one squirrel? Oh my goodness.
I think once I end the poll, probably everyone can see, hopefully. Breaks are kind of funny on Zoom. It's been hard to figure out, like, should we just, 5-minute break, 10-minute break? I mean, people can always go get coffee in the middle anyway, right? It's not like it's bothering anyone.
Yeah, I mean,
but I guess we don't want to lose the content.
is anything real? Really? Anonymous attendee says WSL2 didn't work. Tell me more.
So out of 53 responses so far, almost 2/3 have Docker working. Another 15% are working on it. Only 2 no's. So, and several haven't tries or not sure. 2 squirrels now.
2 squirrels. Yes, yes, we're winning. Okay.
Should we start up again?
Yeah.
Let me, I'll end the poll. Not everyone replied, but that's all right. I mean, this was just to get a rough sense. So can you see that? Oh no, I have to share. All right, hopefully everyone can see that.
Yes, no, not sure. Haven't tried working on it. 15%, 9 people. We have an hour. Let's try to get at least a few more people on. Let's spend the next 10 minutes trying to resolve issues, and let's do this over Slack. So we're gonna, there are dedicated channels on Slack, Docker install help Linux, Docker install help Mac, Docker install help Windows, where you can explain if you're working on it and you get stuck with a particular problem. You can explain what the problem is, and we can all, because I can see that majority of us got it running, we can all help out getting at least some of these 9 people up to speed. Someone was saying that VSL2 didn't work. Yes, and that might be because you don't have the latest update, and you just make sure that you're running the 2020 spring update of Windows 10. There's also someone mentioning that the I see things changed. The Windows Home without an update is still a painful story. Yeah, I don't think within this timeline we'll be able to get Windows Home users that do not have the update yet running. Okay. What version are we using for this tutorial? Virtual ask. Well, it depends on what version of what, really. Oh, stable or edge, doesn't really matter. Okay, stable is perfectly fine. Docker version. Stable. All right, thank you. And let's do stable. Stable, okay. This quick tip for the Windows users, if you, well, it's not gonna work for now, but if you haven't gotten the update now, and after this tutorial finishes and you still want to get the update quickly, you can join something called the Windows Insider program, which will basically send you unreleased versions of Windows on a regular basis, and then it basically always will be on the cutting edge. Which in theory is less stable and definitely involves updating your system much more often. But I've been running it for a few years now, and it's perfectly fine.
Do you want me to run another poll?
Let's see.
How
much space will you? Fahad is asking how much space will we need? Probably somewhere around 8 to 10 gigabytes. Rennie said, I was able to pull bits F-base FSL. Yay, go Rennie. All right, it's fantastic. Yeah, let's give it a couple more minutes. Anonymous is asking, is there an easy alternative to -ti with Singularity? That's what my resources have installed. Don't quite understand the second part of the question, but we're going to talk about Singularity at some extent later, so maybe we can get back to this. Can you please say again what should they do after installation? Okay, so after installation, let me just do this, and so there's chat as well as Q&A. What is this craziness? Okay. What am I sharing now? Okay. All right, so you should be able to see my terminal. Tal, can you see my terminal?
Yes, I can see it. Sorry,
Right.
I was muted.
Cool. Awesome, thanks. Yeah, so after you install Docker, you can type docker info, and you should get something like this.
Looks like progress. I think a few people have moved from the working on it / not sure or haven't tried columns. So probably in the interest of time, probably best to go ahead anyway.
Sorry, say again?
I think in the interest of time, we should probably go ahead anyway. Unfortunately, I guess, you know.
All right, yeah.
Unfortunately, not everyone can get it running, but you can always come back later.
Let's do it. And Tal, is this text legible?
Yes, at least for me. I think I'm on a laptop, so probably for everyone, I guess.
All right, great. So we're gonna be moving forward, and we're going to be following the script on the website, and I'm going to be updating which steps we're on Slack. So if you ever get lost, that's where you should go. Okay, cool. So we are on step 3 because we talked about theory and install Docker, and this is it. First thing we're gonna do, we're actually gonna download an image. So one sort of confusing thing with Docker is that you don't go to a website and you don't click a blue download link and save it somewhere. Docker is actually managing all of the images for you. So you need to use the command line and use the Docker command line to actually download images. And they're identified by their names, not by URLs. So we're going to type docker pull bits / base FSL. Like so. Oh, that's weird. I think I know what's going on. Cool. All right. So we're going to download this. You didn't have to log in. This is just the weirdness of my setup. In your case, you're probably going to see a bunch of things downloading here. And this is because I've downloaded before. So if we do another one, for example, here I'm downloading an image with SPM in it. This is how this experience looks like. It's downloading a bunch of things. And what's actually downloading here are different layers of this image. And this is interesting because those layers can be actually used between different images to save space. So if there are redundancies in terms of what is installed in different images, you can save space by sharing layers of these images between each other. So hopefully this pool works for you. I'm going to interrupt it in the interest of time, because we have this downloaded. So once again, it's there. And if you are interested, you can always, what images you have downloaded, you can always type docker images, and this will show you which images are downloaded on your machine and how much memory do they take. Okay, so the next thing we're going to do is actually going to go inside the container. So let me show you that here in this terminal. If I type bet, I say I'm getting command bet not found. Did you mean ben, bget, bst? Well, bet is not there. FSL is not installed, basically. FSL mask is not there. I'm on my host machine. I don't have FSL here. But if I go inside the, if I basically spin that image and I run this bit space FSL container, I should be able to access FSL software in it, because this image already has FSL installed. So we're starting with taking an image that was made by someone else that has certain software in it. And later we're going to show you how to build your own images and install whatever software you want in it. So we're going to type this, docker run -di --rm bit space FSL. So quick rundown of what this command does is we're running a container. -ti means that it's a terminal style, so I'm going to get a prompt, a shell prompt, and it's interactive. That's the I for. And --rm means that when I exit the shell, the container will be destroyed. The image is still there, but the container, that instance of a class, will be destroyed. And then bits / base FSL is the name of the image I am running a container of. Okay, and now you've noticed, hopefully, this difference of the prompt, the way the command line looks like is slightly different. Before I had it saying me at MSI somewhere, and now it says root at E3, E6 for da da da. So that means that I am now inside the container. Okay, So I would like you to do this and play around with some of these questions that I set up for you in the exercise. So if you go to the website, there are some questions such as, what user are you inside the containers? The same as a host computer. Can you run FSL tools such as PET? Can you access files on a host computer? Create some files, get out of the container, run the container again. Are the files still there? Is there a data folder inside the container? I would like you to figure this out and yeah, and basically post the answers to those questions in whatever way you feel. It's either Slack or Q&A or chat. Just play around with it.
Hey, Chris, I can't see all of your, the whole document. I don't know if that's deliberate or.
Oh no, what about now?
Sorry, I wasn't, yeah, there we go.
Yeah, if I move it outside of the scope, then.
Sorry about that, folks. There's a question about what the TI flag is doing.
Yeah, I just saw it.
We're up to 3 raccoons now.
Oh wow!
But I guess raccoons are more popular than squirrels.
Okay, I don't see the answers. Where are the questions? Yes, the questions are getting inside the container. Yes. Yeah, I don't see answers. Question 1, I am root. Sounds like I am Groot. Yes, that's correct. We're all root users. How do we check user? Yes, which means that you are root. That thing before the @ sign is the name of your username. Candice, question 2. Yes, FSL tools work inside the container. Fantastic. Question 3, Steph, tied with Sanu and tied with Leah. And the answer is no. Can you access files from localhost? No, that's correct. We're going to learn how to do this. Okay. Okay. I can access external files. Yes, that's correct. And question 4. no, and question 5, no. If you get outside of the container, run the container again, are the files still there? No. Is there a data folder? No. Okay, let me show you this very quickly. So bet, yes, I can run bet. I'm root. And then finally, let's, I am in the root folder, and I will create a test file. Create the test file. The test file is here. Now I'm gonna exit. Now I'm gonna run it again. And I will do this, and the file is not there. And also there's no data folder. So how can I run FSL tools? Well, from the command line, as I showed, you can run vet, or you can run FSL maths. The -ti question was answered. So look at the answered questions, and then there's the explanation. Okay, can access, this is done, this is done. We are root users, that's great. Okay, cool. So we blazed through this. This is great. I think hopefully everyone got everything. So now we're gonna actually learn how to access local files. So we're gonna create a folder. We're gonna create a folder on our local hard drives. I'm gonna exit this container. And I've created this folder. It's called home, me, Docker tutorial. And inside this folder, I'm gonna store some files. So we need a nifty file. How can I do this? So I could see both things at the same time. Okay. Give me a second. I'm just rearranging stuff so I wouldn't cut you off. Okay, I see it. Okay, so many messages. Okay, yes, okay, I see. All right, cool. And yes, sorry. I just had to rearrange some windows just so I would be able to see all of your lovely messages at the same time. Okay, so we're gonna need some nifty files to work with. If you have some, you can just use them. But you can also download something from Neurohackademy. So this is what I'm going to do now. All of the things I'm doing are explained in the tutorial on the link I've sent you. So I'm going to download a file here. So I downloaded a nifty file. Over here, I can show you that I have indeed a nifty file in this folder. And I'm still on the host machine. This is where it is. And now what we want to do is we want to run the container. So run the container, but we want to specifically tell it that it can find some subset of our local files under a specific path. So this is called mounting a file system. but you can think about it as creating a link, in other words. So the full command for this is this one. So let's go through it. So it's only one change from what we used before, and it's -v followed by a local path on the host machine, followed by a colon, followed by a path inside the container. So this means that I want to map the host machine folder, home me Docker tutorial, to inside the container path called data. And I want to run this container. So let's see whether this works. Sorry, I forgot to type Docker. Okay, so far looks the same, but now if I do ls data, I see the contents of that folder. And so let me just walk you through it again. Walk you through it. I am on my host machine. Yes, Augustine asked whether this is a link to the data, not a copy. That is correct. This is a link to the data. Let's work through this once more. I am on my host machine inside home me Docker tutorial folder. And inside this folder, I have this nifty file. If I run my container without mounting anything, like so, and I do ls data, it says no such file or directory. But if I now use the -v followed by the host path colon followed by the container path, I will mount this file system or make a link, in other words. So I do this, I do ls data, and now I can see this file. And just to show that this is a link, if I go to the data, and now let's say I want to create a new file here. I've created this file, and now I am getting out of the container. I own the host system. And the file is there. So it's a link. So anything you change there or create inside the container will also affect the outside of the container, and vice versa. And now one more thing that I want to show you is that after the colon, that path here, it's kind of arbitrary. So I can just type squirrel here. And now data is not there, but squirrel is there, and it has my data in it. So it's just a placeholder. It's basically a path that you can define, and will create this virtual folder for you with the data out there. So hopefully this makes sense. I will answer the questions now, and you can if you're already done with this, you can follow the instructions at the end. There's an exercise there with using FSL math. So Anonymous asks what to do if wget and run commands not found. Okay, well, it means that you don't have wget installed. That's fine. You can just download the file via web browser. And then we also have a question on Slack. Is there a nice way to provide relative path as arguments to -v and typical? okay. Last time I checked relative paths and Dash didn't work with Dash V. Okay. Okay, so Albert asks how to save state in a container so pick up when you left off. What happens if host crashes? Okay, so there are a couple of things here. You can indeed remove the -- rm option from it, and then the container will keep running. And there are some ways to take that container and turn it into an image. What I recommend is basically mounting your source code or your scripts inside the container, as well as your data, and have the build process of the images in a reproducible way, which I'm going to show you next. So this way, if anything crashes, you can basically reboot and get back into it, because the container only has all of the dependencies, but all of the data and all of the scripts that you've been modifying and working on are being mounted via -v. Hopefully this answers your question. And Ben says yes, 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 which I presume are the answers to the questions. And the exercises were, can you see downloaded map in the data folder or in the squirrel folder as we just did right now? Let me just go back to the data one. So ls data, there we go. And now, can you use tools installed in a container on the files in the data folder? So can I, for example, use FSL Math to smooth this thing now inside the container? Yes. So ls data, and now I have the smooth file here as well. And now if I go out, I still have this smooth file here as well. Okay, thank you, Ben. And now Sanu says, I couldn't find the file in data. Well, let's debug this on the Slack channel. If you can post on the Slack. Oh, sorry, there's a follow-up. Yeah, exactly, Tinashe, thank you. If you could post on the Slack what your command is and what was the output, we can help you figure this out. Anonymous asks, when I'm inside the Docker image and I try to run Docker run, it tells me Docker command isn't found. Any idea why? Yes, because you are inside the Docker image and inside the Docker container. And unless Docker is installed inside this image, you won't be able to run it. And it is sort of like a advanced kung fu to have Docker in Docker, but this is not what we're doing. Docker is installed on your host machine, and that's why you can run Docker there, but it's not installed in this particular image. You can get an image where it is installed, and then this will work. Okay. Alison, can you talk a little bit more about the default files, bin, boot, def, etc. that are automatically created with the container? Okay, so this is a very sort of long topic because all of these different folders and files are this standardized folder structure of a typical Linux distribution. And I will try to follow up with this, providing some links that will help navigate through how Linux distributions have their files arranged. This is nothing really specific to Docker or containers. It's basically how files are arranged in Linux. Davide asks, how do we set up our Docker image from scratch without starting from one like base FSL in a similar fashion to virtual for user environment and install the libraries you need? That's an excellent question, Davide, and the great segue to our next stage. Before we go there, key points from here. Container images are downloaded from Docker Hub. You can run shell inside the container, and only explicitly mounted host folder are accessible inside the container. And we can go to the next stage, and I'm going to post it, which means create. Okay. So let me just post this very quickly. Okay, cool. So now we've run an image, we run a container, we download an image, but what if we need to modify it? What if we need to basically add something, or we need to create something? I'm going to show you how we can actually create a recipe for creating our own image. So Docker images are creating from these, based on these files called Docker files. And we're going to create one, and we're going to build a custom container when we control what's inside it using it. So as some of you might notice, what I'm presenting here is not just a terminal, it's actually a text editor, a very nice one called Visual Studio Code, but you can use any text editor you want. So what I'm gonna do now is I'm gonna create a new folder. I'm gonna call it Docker, and that's fine. And inside this folder, I'm going to create a file called Docker file. Okay, so, and inside this Docker file, I'm going to basically copy paste the text from our tutorial. It starts with this line called from bit/base/fsl. And all images in Docker have some sort of a base. So they're all created from some other image. Right now, we're gonna use the image that we used before, but you can base your image on many different existing images out there. And if we have time, we're gonna go to Docker Hub. We'll show you how to browse through images and find what you need. And those images can be very rich, as in they can have a lot of different software and be very large, or they could be very, very slim, only a few megabytes and have bare bones. So this from directive here tells you which image should we base this on. And now what we're gonna follow this by is another directive called run. And this run directive basically runs a shell command in this recipe. It just, whatever is after run, it will be run in shell. And here what we're doing, we're downloading Miniconda, which is a Python installation, into a file in /opt/miniconda. Okay, and then what we're gonna do is we're gonna do run, and we're gonna run Conda installation that we just downloaded. there's some options there related to Conda, and we don't need to go through there. Basically, the first run downloads the mini Conda installation package. The second command installs it. And then finally, what we're gonna do here is we're gonna update environmental variables inside this container to make sure that Conda is accessible from the shell. So the big takeaway here from writing these recipes is that they're extremely powerful because you can run whatever command you want here. But the downside is that you have to know what to run. So you have to know which Linux distribution you're working with and how these commands should look like for them to work. But maybe it will help to actually take and build this image. So I'm going down to the terminal here. I'm gonna change directories to my folder where the Docker file is, and that's important. The next command I need to run from the folder where the Docker file is, because the dot is here at the end. So I'm gonna run docker build -t, which is the tag or the name of my image, my new custom image. I'm gonna call it FSL with Conda, followed by the path to where Docker should look for a Docker file. And I'm using a dot here because that's the current working directory. But before we run this, let's do the following. Those are all the images I have. Well, actually, I do have an image from, let me just Docker. Sorry, I was testing all of this before we started. So right now I don't have FSL with Conda image, but I'm gonna build it now. So let me just copy this file again here. Docker build. And now it's downloading Conda. It's finished downloading Conda, and now it's running the installation. You can see the step 3 out of 4. This is the third line of our recipe. This is what's going on right now. And it's extracting and installing Conda, which is a Python environment. And now it's done. So let me show you now. If I do Docker images, I can see that there's a new image, FSL with Conda, that was created 13 seconds ago. I just built it. So if I do Docker run ti FSL with Conda, I got Python inside my environment. Okay, so let's stop here and see what questions do we have. Some of these questions are not related to this step. I'm gonna go through them later, but don't worry, I'm not gonna forget. Okay, what is happening in the background while we do this? An example, what does transaction and intermediate container mean that are removed? Okay, I think you might be referring to the output of some of the commands I ran before when I was removing an image. So this is a little bit of an advanced topic, but basically each time one of these commands in this recipe is run, a new layer or basically a binary difference is created. And those layers, if they're identical across images, they're being reused. So the binary data is not being duplicated and thus saving space. So when I remove an image, what Docker is doing, it's going through these different layers and making sure that when I remove this image, it will remove all of the layers that were part of this image that are not being used by another image, so it wouldn't break anything. And hopefully this answers your question. Gergen asks, the point in this row means that we build containers from files in this folder. Yes, when you say the point, you're referring to the dot at the end here. So yes, that's what it is. So in other words, I can go to a folder one up and do docker fsl with conda build docker, and it will still build. It's basically a path. Okay, do you have access to FSL in the image you just created, given it's based on base FSL? Well, let's check, right? FSL, yes, I do. And that's how you can basically build upon existing things in Compose. And actually this image was built explicitly with this intention for people to be able to add on top of this. Okay. Then, can you give some resources to more in-depth on making Docker files? Yes, I will share that on Slack when we're done. Is there a way to show the directory path where the Docker containers are saved? Alex asks. This is a little bit complicated, especially if you're using Mac OS X or Windows, and depends on your setup. I will try to dig it up. I don't know the answer on top of my head, but I'll try to get back to you on this. Okay, we have some exercises to do afterwards. So I would like you to follow them. We already checked whether you can run Python inside the container. Yes. What happens if you run the build command again? So I just did this. So I can just do it exactly the same way, so it'll be less confusing. Whoops. So when I run this build process again, basically it's very, very fast. And this is because you probably noticed it's saying using cache. So all of these layers are being cached. So if I haven't changed anything in the recipe, it's going to use this cache. But if I do change something, then the cache will get invalidated. So in other words, I can, and this cache is based on the hash of the text. So I think even if I added a blank space here, this would invalidate the cache. Let's have a look and see whether this works. Yes, so I've changed something in the recipe, and all it takes is change one character in this line for this layer to be recomputed. And all of the subsequent layers will be recomputed as well. So it's caching, but it's not like extremely smart. But the next two questions, could you modify the Docker file to include extra Python packages? That is an exercise for you. I would like you to quickly try doing this. And when you do it, share your Docker file in the Slack. And I'll try to answer some questions in the meantime. Can you build a container for multiple images? Say one build FSL and ants. I can find one with both. I don't. Well, the short answer is no. There needs to be one single base. There might be some composing features recently added. I haven't used them, but in general, when you're trying to combine multiple things, you have to basically create your own Docker file and install everything you want in it, which takes some work to like figure out all the steps. And there are some projects such as Neurodocker, which I'm going to share with you now, that allows you to automatically generate a Docker file with specific neuroimaging software that you might want to need. So I'm going to share this. Okay, Neurodocker. Okay, is there? Do you have any recommendation for running? This is a different. GUIs. There are 2 questions about GUIs. I'm going to answer them at the end. Okay.
Chris, just to go, we probably want to leave like 5 to 10 minutes between. So if you want to start winding down, and maybe like wrap up in like 5 to 10 minutes max.
All right. Let me just, did anyone manage to install packages inside their Docker file and want to share the Docker file with us? Don't be shy. All right, let's try this. Run Honda install Seaborn. Let's just do this. So we added this line, and now we're gonna have not only Python and FSL in our environment, but also we're gonna have Seaborn, which is a visualization pipeline inside it as well. And it's hopefully gonna finish very quickly. Okay, I'm gonna answer the GUI question right now. So is there any possibility of viewing GUI with a Docker container? Yes, there is. It's called X server forwarding. So you need to install an X server on your host machine and then forward it from the container. It's not very easy. I'll try to dig up some instructions on how to do this. If you could repost this question on Slack, that'll make it easier. It's not straightforward and the experience is not great, but it is possible. If you repost it on Slack, I'll try to follow up there. Okay, so now let me just quickly show you that this works. So I can do Python. And we have Seaborn. All right. So in the interest of time, we're gonna move on, and I'm gonna show you how to share images very quickly. So you need to create an account on Docker Hub to be able to do this. Docker Hub is this repository of images. All images are public in the free tier, just a big disclaimer, but well, I mean, don't share any secrets, basically. So first thing we have to do is provide our credentials to Docker. So I'm going to do Docker login, and I'm already logged in. Otherwise, we'll ask you for a password. And now to be able to upload your image to Docker Hub, it needs to have a specific file naming convention. And that file naming convention means that it's your Docker Hub username followed by a slash followed by the name of the container. So I'm gonna retag the image we've built already with this name. I'm replacing this placeholder with my actual Docker Hub username, which is Philo, because that's cool. And this retagging, basically changing the name of the container, it doesn't use up any space. It's instantaneous. It's basically creating an alias for this container. So now that I've retagged it, I can actually push it to Docker Hub. So now I'm actually uploading this image to Docker Hub. And this is taking a little bit of time because we're streaming and doing other stuff, and my internet is not as fast as it used to be. But I can show you how this looks like on Docker Hub. And to do this, very quickly navigate to Docker Hub and show you. I've uploaded this image before. So let me share a new screen. Okay. All right, cool. So this is Docker Hub, how it looks like for me. And this is an image I've created recently. And there are many options here, but I can basically, now anyone can do Docker pull philo/fsl with conda, and they can download my image. So this is a great way of sharing images with others and with yourself as well in the future, because you can put it in this repository and it will stay there. Okay, and next, we're running out of time a little bit, but there were questions about Singularity, and I want to cover this a little bit. So a little bit of theory. We talked about Docker a lot because Docker makes it very easy to create, manipulate, build containers on your own hardware, on your laptops, on your Windows machines, on your Mac OS machines. However, Docker is optimized for running services in the cloud where those are not multi-user servers. So there's like one administrator that admins them, which is different from how high-performance computing systems are designed. So your clusters, your compute cluster, have multiple users, and many users access those. And Docker is just not designed to handle this type of security very well. To be able to run Docker images on high-performance computers, you need to use technology called Singularity. So think about Singularity as a way of running Docker images on high-performance clusters. And that hopefully answers the question, which one should we choose? I recommend building images using Docker and then running them on clusters using Singularity, because in most cases, you will not have the option to run Docker on a cluster. So you need Singularity to run Docker images on a cluster. And sometimes you might not have Singularity installed on your cluster at all. And then you will have to basically ask your administrator to install Singularity. And there are different resources on how to convince your admins to do this. Many clusters already have Singularity, including some at the NIH. So it's a fairly popular and proven technology. But I can show you how I can run things on Singularity. And okay, cool. I will do this. Yes, so I will switch screens again and share a different terminal, and it might look It might look very similar to.
I think I'm going to have to stop, unfortunately, just because in 5 minutes there's 2 other sessions starting.
Okay, well, anyway.
One last final super important thing.
Yes, so this is how you can run a container that I've just created and will be downloaded automatically from Docker Hub. And here I can do pet and all that other fun stuff. And this is how you can run on a cluster. So we have a lot of unanswered questions. I'll try to answer them here. Will this remain, Tal, this Q&A?
Unfortunately not. I think there's a way we can export them later, but maybe better, that might take us a while because both are on our team.
Okay, all right, guys. So we're running out of time. Please repost your questions on Slack. I'll go there and answer them. It might not happen immediately because I need to go to work in 4 minutes, but I will get back to you eventually, and we'll resolve this. I had a lot of fun. Thank you so much, and enjoy the other session, and see you on Thursday.
Thank you, Chris. Appreciate it.